Oh, Atom here, welcome back to some more... Wait a minute, this is the Kerbal Space Program. Anyway, so last stream I showed off some stuff for setting up a relay network, but made a mistake with some of the maths. So, take two. We have 3 relays, and we want to ensure we can always phone home. If you're on the planet, and the relay's in orbit, and the relay's orbit is too low, you might be able to talk to the relay above your head, but it also has a planet in the way. So, you want relays to be able to talk to each other. They also can't talk to each other if there's a planet in the way. So, let's draw some lines to see how high up our relays need to be. Now we have a triangle. The minimum height of our relays means that the edge of this triangle touches the circle that is the planet. Any lower, the relays would need to talk through the planet. So, let's find the minimum height. Little r is the total radius of our relay orbit. The big R is the radius of the planet. Not quite enough info. Our relays are equidistant, so we have an equilateral triangle, which means that the interior angle is 60 degrees. Split that in half, and we get the right angle triangle with an angle of 30 degrees. So, trigonometry time! Sine is the opposite over hypotenuse, and we know the angle, we know the opposite, so we can find the hypotenuse. So, the orbital radius is going to be the radius of the planet divided by the sine of 30 degrees. Now, 30 degrees is a simple angle, along with 0, 45, 60, and 90, and the sine of these angles is going to be incrementing roots divided by 2. So, sine of 0 will be square root of 0 over 2, well, 0. Sine of 30 will be square root of 1 over 2, or a half. 45 would be square root of 2 over 2. 60 would be square root of 3 over 2. And 90 would be square root of 4 over 2, which is 2 over 2, which is 1. So, continuing on, sine of 30 being a half, we can simplify our result, and we get a minimum orbital radius of 2 times the planetary radius. So our minimum altitude is going to be the same as the radius of the planet. However, planets are not perfect spheres, and your relays won't be perfectly equidistant, so you'll want some extra buffer room. The true minimum would be the planetary radius plus then the height of any of the tallest mountain, but what you'll see on the planet info within KSP is just going to be the planetary radius. So Juno's radius is 320 kilometers, which means that the minimum altitude would be 320 kilometers. Just to be extra safe, I've decided to go with 640 kilometers. Now, let's go over orbital periods, or how to actually get the relays into their position. Suppose we have a circular orbit like this. The period of this orbit will be 2 pi times the square root of the orbital radius cubed divided by the standard gravitational parameter. I'll explain this A in a moment, but the standard gravitational parameter, it's sometimes written as mg. Sometimes written as mu, as I have here, but also sometimes written as big G times big M. KSP, you'll see the latter. What is it? It's the gravitational constant big G, so universal gravitational constant, times the planet's mass, big M. Yeah, that's why it's sometimes written as GM, it's G times M. Basically, it's a pre-calculated constant that appears fairly often in calculations. And because we often know G times M to a lot higher precision than either G or M, GM tends to be used. Now, suppose we increase our orbit to this new ellipse. We keep the same periapsis. What's our new orbital period? This is where the A in our formula comes in. A is the semi-major axis, and quite simply it's the average of the periapsis and the apoapsis. And it turns out that the period of an elliptical orbit is exactly the same as a circular orbit with a radius of the semi-major axis. So, have this inner circle, that's our starting orbit, then create a new orbit, which is this larger ellipse. This larger circle, which is halfway, which has, it's a radius halfway between the first orbit and the ellipse's new apoapsis, that has the same orbital period as the ellipse. So, if we want to separate our relays by 1/3 of an orbit, we want to be in a situation where our transfer vessel has an orbital period that's 4/3 as long as the circular orbit. So, let's plug in the numbers and simplify both sides of the equation. U pi cancels out, as does the square root of 1 over mu. Square both sides and then take the cubic root. We have a constant times a. Let's break down the semi-major axis into its apoapsis and periapsis on both sides, and move the periapses to the one side. We then get the orbital radius of the apoapsis in terms of the orbital radius of the periapsis. Keep in mind that to get the altitude, you need to subtract the planet's radius. Given the target values we have for Juno, this means that I'll need to aim for an altitude of roughly 1,045 kilometers. So notice that we still had 4 over 3 in the middle of our equation. If you want some other multiplier k of an orbital period, if, for example, you want to organize a rendezvous, or you've got more than 3 satellites, or more than 3 relays that you want to put into equal distance orbit, well, you can just plug it into this formula. So this would also work if you want to go for 2/3 of an orbital period. I tend to go for larger rather than smaller, just because sometimes if it's a small enough orbit, you're then having to deal with atmospheres, or potentially hitting large things on the planet, large mountains. So that's why I tend to go higher, but if you're high enough up, then you can go smaller. Now, for a bonus section that wasn't on the stream, since you have your relays in orbit now, you want to make sure that you can actually phone home. Wait, that doesn't seem like the right order of things. Anyway, communication is not a one-way street, and signals have a max range. Max range will depend on the antenna power of both vessels. Max range in meters is the geometric mean of the powers. That is to say, it's the square root of the transmission powers that are multiplied together. So P1 times P2, take the square root, that will give you your max range in meters. You can combine multiple antennas. So, for example, you have 2 vessels with the built-in command module, which has 5K antennas. The maximum range would be the square root of 5K times 5K, which is just 5K. So your max range would be 5 kilometers. Now, 2 vessels with command module antennas won't be able to talk to each other. Get to that soon, the relay section. Yes, you can combine multiple antennae on a single craft to boost the transmit and receive power, but you'll get diminishing returns. So the net power that you get is going to be the power of the strongest antenna, then multiply that by the sum of all the antenna powers divided by the strongest antenna. Then you take that to the power of the average compatibility. So what is this compatibility? Well, with 2 exceptions, every antenna has a compatibility of 0.75, including the default 5K antenna that's in each command module. To get the overall average compatibility, you multiply an antenna's power by its compatibility rating, and you add all these together, then divide by the total power. 2 exceptions The first one is the Communitron 16, which has a compatibility of 1.0, and the Surface Communitron 16, which has a compatibility of 0. So adding multiple Communitron 16 Surface aren't going to really improve your isn't going to improve your range by much because you're decreasing the compatibility rating. So let's go with an example. If we have a probe with two Communitron 16s, two Communitron 16S, and two high gain relay antennas, and we're using it as a relay, well, since we're using it as a relay, only the high gain antennas can count, because they're the only relay antennas on the satellite. In which case, we've got 5M plus 5M, we've got a total of 10M. For average compatibility, for the average compatibility, we multiply the 5M by the 0.75, the typical compatibility. Multiply that by 2, and then divide by 10. Get 0.75. That's how averages work. If you're only with relay antennas, you're always going to get 0.75 because all your relay antennas have a compatibility rating of 0.75. So, total power you have from these two relay antennas is going to be 10 divided by 5. Take that to the power of 0.75, and then multiply that by 5. So 2 to the power of 0.75 times 5 gives you 8.40896 M. So you have two relays with this power. Maximum distance apart they can be while still communicating would be 8.4 megameters, or 8,409 kilometers. So, if we aren't using the satellite as relay though, and we want to talk back to the KSC, well, the highest power is 5M from those high gain antennas. If we take all the antenna strengths, you get 5K from the probe core, plus 500K times 4 for all of the Communitron 16s, then 5M from the relay antennas. That all adds up to 12.005 M. Want to look at the average compatibility? We've got 5K times 0.75 for the probe core. We've got the Communitron 16s with the compatibility of 1. We've got the Communitron 16s with compatibility of 0. Then we've got the high gain relay antennas. And all of that will be divided by the sum. So 12.005. Work that out. The probe core gives us 3.75. Okay. The Communitron 16s give us 1M. The surface ones give us 0. And the high gain relay antennas give us 7.5M. Divide all of that by 12.005. We get about 0.708. Now, to get our total power, we take the sum of the powers, divided by 5, which is our largest power, put that to the power of our average compatibility, and then multiply that by 5, and we get 9.29 M. If, however, we remove the the surface Communitrons, you see it is a bit less. It's about 0.1 M less. Go between the two. It won't impact much. Adding multiple doesn't add much benefit because you're decreasing the average compatibility. And if they're your only, if you don't have a larger antenna, then they're going to be decreasing that average compatibility a lot more. So, if we also ignore the command module to simplify the expression, you can see we're still getting 9.29. It doesn't impact the result much. Certainly it is adding a bit, but it's about 0.003 M in this example. So yeah, when you're dealing with larger transmissions, then the probe core doesn't matter much. Same with the command modules. They've also got the 5K, you know. Anyway, so for relays, your probes will need a connection to your space center in order to control them. There is one exception where there's a core that can control other nearby remote devices, but I'll ignore that for now. For the most part, you'll need a connection to your space center. Now, this could either be a direct connection, or a connection to a relay satellite that's connected to the space center. And this can keep going. This is recursive. You can connect to a relay satellite, it's connected to another relay satellite, that's connected to another relay satellite, so it's connected to another relay satellite, that's then connected to the space center. But as long as there's a chain that can bring you back to your target vessel, you will be connected. Relay satellites, however, only calculate the transmission power of their relay antennas when used as a relay. So every connection needs to go back to the KSC, but then what's the transmission power of the tracking station? Well, it comes in 3 levels in Career mode. If you're not playing in Career mode, you'll have a level 3 tracking center. Level 1 is 2G, and you can see it's a smaller version up here. Level 2, it's 50G, see a slightly larger facility. And at level 3, it's 250G. You can see the final facility down at the bottom. Now, for relay distance, we've determined how high up you need to put your relays. We know how far relays can communicate to each other. So then what relay antennas do you need to put on your satellite in order for them to talk to each other? So again, let's bring back trigonometry. Krakatoa. Half of this distance here, well, we've got our orbital height, got an angle here of 30 degrees. We used sine last time, so we'll be using cosine this time. So, cosine of 30 times the radius will give us our adjacent value, which will be half of d. So in order to find the distance between the 2 relays, we just multiply that by 2, so 2r times the cos of 30. Cos of 30, as we mentioned before, 30 is one of those important angles, one of those easy angles. Cos of 30 is going to be square root of 3 divided by 2, so 2's cancel out, and we're just left with the orbital radius times the square root of 3. For our example, where we have a target orbit of 960 kilometers, it's going to be 960 times the square root of 3, which is about 1,663 kilometers. So, relays would need to just be able to talk within the system, talk to each other. They'd need a power of at least 1.663 to communicate with each other. 1.663 M. This isn't so much relevant for interplanetary stuff, because if your relays are able to talk to each other, or if your relays are able to talk to the KSC, they're probably going to be able to talk to each other. It can be an issue early on, if you're using a low-level... Well, not if you're using low-level relay, but if you're using low-level antennas around the moon or around Minimus, for example, or if you've put them into a higher orbit. Yes, it's just something you need to keep in mind in that case. It can be quite useful to choose a relay power so that at the planet's surface you'll be able to communicate to the relay using only the command module. But yeah, you would just plug it into the equation from before, so you get the geometric mean of 5K and whatever relay satellite would need to be. One final thing, I won't go into too much detail, but signal strength. With a high signal strength, you can get up to 40% bonus with transmitted signs. I've with high signal strength twice in that sentence, and was like, oh well. But basically, if you take x as 1 minus the distance between your relays and the maximum range, then the signal strength value will be negative 2x cubed plus 3x squared. X will be between 0 and 1 for this formula. And when if you're bouncing it through relays or multiple connections, the overall signal strength will be the product of all the signal strength steps. If you're interested in it, I would recommend looking that up yourself. But in any case, I hope you've enjoyed. Let me know any feedback you have in the comments, and until next time, see ya.